Gibbs free energy, and equilibrium. So yes, we're connecting what we learned about with thermochemistry and Gibbs free energy, that delta G, to the concept of equilibrium. So first we're going to start with a little analogy. We've got this ball and it's rolling down this hill into a valley. But you see, as we go back up, as we go past the valley, it goes back up. So the lowest energy position here is at point C. The ball could roll down from A to C. It could roll down from B to C. But either way, there's a sweet spot, a low point. Remember, low energy is stable. Okay, well, let's put this into context of if we, say, had Gibbs free energy on the y-axis here and our reaction progress on the x. So at point A, if we have all reactant, Gibbs free energy is going to be rather high. And if we have all product, Gibbs free energy could be rather high. But there's a sweet spot at which it reaches its absolute minimum and is spontaneous, because Gibbs free energy is less than 0 at some point. Well, at that reaction, that is also going to be a point for equilibrium. Okay? So if we think about this, none of A has reacted. We have very high Gibbs free energy, and as some of A reacts, then we get more stable. And if we do it from the other side, we get more stable too. Okay? And so then there's a sweet spot where equilibrium occurs and Gibbs free energy is at a minimum. Okay, so you can see all that close up. Okay, now that might lie closer to the products, it might lie closer to the reactants. It depends on what it is. Okay. But here we've got a little relationship. If K is much greater than 1, we're going to see that delta G is less than 0. Okay, so if K is much greater than 1, that means we have a very product-favored equilibrium. And the reaction is going to be spontaneous in that it goes from reactant to product without outside intervention. But if K is less than 1, the reaction is probably not very spontaneous. Delta G is greater than 0. It's positive. So let's actually put that into a table. Okay, and let's add in this. When K equals 1, we're at equilibrium, and neither reactants nor products are favored, and delta G is equal to 0. But if K is greater than 1, we're going to see that delta G is negative to reflect that this reaction is spontaneous and will proceed towards the products. Okay, so we need to know this a little bit theoretically, but we also need to be able to do this in terms of a calculation. And here's our equation. Delta G, so Gibbs free energy, equals negative RT natural log K. Well, R, this is that ideal gas constant, 8.31 joules per mole Kelvin. It's in your part 2, the second page of your data booklet. This whole equation is in the first page. T is temperature in Kelvin, and natural log of K, our equilibrium constant. So let's try an example. The esterification reaction that produces ethyl ethanoate has a free energy change, delta G equals negative 4.38 kilojoules per mole. Calculate the value of the equilibrium constant of this reaction at 298 Kelvin. So here's our equation. Now, remember that R is just in joules per mole, and Gibbs free energy is in kilojoules per mole. So we're going to need to change one of those. Today, I'm going to change kilojoules to joules. So I'm going to multiply 4.38 by 1,000 to get to joules, and then I'll plug in my R value and my temperature in Kelvin, make sure it's in Kelvin, and then we don't know what K is. Well, I'm going to solve this a little bit. So negative 4.38 times 1,000 divided by the product of these guys gives you 1.77. Well, how do we undo a natural log? We use Euler's constant. Remember that little lowercase e from that's on your calculator. So e to the negative 1 point, or to positive 1.77 will give us k. So go ahead and type that in your calculator, and hopefully you get 5.9. Okay, so these are kind of just a plug and chug. You have to remember that that equation is there. Let me show you a slightly more complex version. This. Calculate the equilibrium constant at 300 Kelvin for the oxidation of iron. And they give us this reaction, and they give us delta H and delta S. How are we supposed to get to the equilibrium constant? Well, we can get to the equilibrium constant through Gibbs energy change, and we can use these two to get Gibbs free energy change. So we're going to find delta G. We're going to use delta G equals delta H minus T delta S. You want to make sure you've got kilojoules, you've got joules, you want your units to match. So I'm going to divide delta S by 1,000 here and plug it all in and get my value for G. And now that I have G, I can find K because I'll plug it in the other equation. Okay. And remember, we're going to use Euler's constant. And K comes out to be 2.6 times 10 to the 129th power. So this lets you know just how product favored the formation of rust is, because that's what this reaction is. It's the oxidation of iron, the formation of rust. So when you see a K that's this big, you really can say this reaction is not reversible. And we generally know that from experience. So there you go.